Well, hello and welcome everybody. Good morning, good afternoon, good evening. You see the audience and participants rolling in. Welcome to the second networking channel panel series. This topic for this bi-weekly event is a journey with millimeter wave research, and we have a stellar panel with broad international representation as well as lots of experience from folks who've been working on this technology for close to a decade, have published a lot of seminal papers on this. Before I jump into the topic, I just want to take an opportunity to at least introduce the networking channel to the audience members who weren't part of the first series. This is an initiative by the PAWR EU Coordinated Support Action, the PAWR Project Office here in the US, and the ACM SIGCOM community to sort of set up a virtual organization that allows our community, which for the past 14 months has been quarantined in their own research lab ecosystems, to come out of the woodworks and really share experiences, updates, and to continue the good work that was happening prior to this new era, and to be able to do that in a nice, consistent fashion with a very broad set of topical themes. So as you can see, these themes are cross-cutting. The first series event was purely about in-network measurement and monitoring, and now we've switched the script to talk about radio frequencies in the 30 to 300 gigahertz space, and we're going to hear from our panelists here. This is also an opportunity to allow folks who are traditionally not available to attend these conferences due to other logistics and travel-related restrictions, but still to hear from the luminaries in the field. So engage with us, participate. This is a bi-weekly series. Visit our website at thenetworkingchannel.eu. I'm Manu Gosain, Technical Program Director for the PAWR Project Office. And for this session, I also want to welcome my co-organizer, Antonio de Oliva at UC3M in Madrid, Spain. And we have put together this panel that's going to be led by Joerg Widmer at IMDEA Network. So next slide, Antonio. Thanks. At IMDEA Networks, and he'll kick things off with kind of where the state of the art of millimeter wave research is in the year 2021. I want to calibrate that this panel is not necessarily about millimeter wave 101. For that, there is a wide body of research that's already been published, and we advise you to go and catch up. This will be primarily looking at what are the most practical considerations for millimeter wave systems in the year 2021 and beyond. What are some of the progress that has been made? What are the key results that have been produced? And now as deployments are happening worldwide, what are the key challenges that the panelists here sort of see? So to engage with us, ask questions in the Zoom using the Zoom chat feature. There's also the Slack channel that we've put forth that you can use for continuing the conversation. The panelists will be available there as well. So please feel free to address your questions, comments, and thoughts there. And with that, I'm going to introduce two panelists representing the United States, and then I'm going to hand it over to Antonio to introduce the panelists from Europe. So without further ado, Professor Sundeep Rangan, who's the director of NYU Wireless at New York University here in the US, again, does not need much introduction, has been working in this field for a long time. He has lots and lots of experience with 4G systems, 5G systems, had a startup, Florian, in 2006, which was then acquired by Qualcomm Technologies. And I don't have enough time to go over all the accomplishments he has. Key ones: fellow of the IEEE and director of NYU Wireless, which is an academic industry research center focusing on next generation wireless systems, millimeter wave, and now looking at terahertz communication. So welcome, Sundeep. And then Xinyu Zhang, who's an associate professor at the UCSD Jacobs School of Engineering at the Center for Wireless Communications. Xinyu's also been working on millimeter wave for a long time. He's received his PhD from Michigan in 2012 and was working earlier at University of Wisconsin-Madison as faculty till 2017. He's a recipient of the ACM Ubicom Best Paper, not once, but twice, in 2011 and most recently in 2020. And I believe we'll hear something about MCube, and also the Google Research Award in 2017. So really excited to sort of hear from these two panelists, and then over to you, Antonio, to introduce Joerg, Michele, and then hand it over to Joerg.
Thank you, Manu. So welcome everyone. My name is Antonio de la Oliva from the University Carlos III of Madrid, and I'm here as a representative of the PAWR project that is trying to build a gap between United States and Europe in these areas of research. So the first speaker from Europe is Michele Zorzi, which is a very well-known researcher in the area, so not much to say about it. He has been working in the University of Padova since 2003, and previously he has been in University of Milano, Politecnico di Milano, in the University of California, San Diego, and the University of Ferrara. Currently, his research interests in millimeter wave are basically focused on the different research projects at the European level on millimeter wave, and also his group is very involved in the development of open source simulators modules for millimeter wave. If we go 1 second to Joerg Widmer, that he is going to run the show, there is a lot to say about Joerg. As Manu has said, we don't have time to go through all his CV, so just to highlight a couple of things. He's now currently a research professor and research director of IMDEA Networks in Madrid, Spain. And just to highlight a couple of things, he has got an ERC consolidator grant, that is a big thing in Europe. And let me see if I'm able to say it properly, the Friedrich Wilhelm Bessel Research Award of the Alexander von Humboldt Foundation, which is also a great honor. So I will now pass the floor to Joerg. Thank you very much all for coming.
Okay, yeah, thanks so much for inviting me to run the panel. Let me see if I can share my screen.
I will stop now.
Okay, now you should see my slides. So I will kick it off with sort of a very brief introduction. I on purpose kept the presentations very, very short because I think the most interesting part is really to have a nice discussion and have like the audience participate and the panelists talk. So I'll keep it short and just very briefly kick it off with where we are now. So of course, I mean, the main purpose why we want to have millimeter wave is multi-gigabit data rates per user that at lower frequencies are possible but hard to achieve, right? You really have to push the hardware. And at millimeter wave, that sort of comes for free because the bandwidth is so large, right? So you don't even have to use MIMO. You don't even have to use high order modulation schemes to achieve gigabit data rates. Now, this has been used in a number of standards, right? It's part of 5G, 6G. It's part of the local wireless local area network standards, 802.11ad and AY. And so that has been around for a little bit. Now it's really at the point where we are seeing information coming back from deployments. So first generation hardware has been out for a while, and that's been extremely useful just to show that you can really deploy those devices, manufacture them at cost in terms of hardware complexity, it's manageable in terms of energy consumption, right? So now, well, there has been this seminal paper from NYU that millimeter wave will work. And now we really know that it does work because we've seen the hardware and it's been shown, because there were doubts before, right? It's a technology that's not easy to manage, and it's still not easy to build those devices. Only a few companies do it, but it is doable. Now, at the same time, a word of caution, 802.11ad, it's been out for a number of years now, four or 5 years in terms of hardware and a bit longer for the standard. And it's not really been widely adopted. And that's certainly something to keep an eye on when you talk about millimeter wave, right? It is a technology that's not easy to manage, and it is a type of network that can be hard on the consumer just because it's a very fickle network, finicky, right? You easily lose the connection. And so unless you really need those data rates, why bother? Why go through the pain of really trying to get that network to work? And that seems to be one of the issues there were with 802.11ad, why it wasn't adopted. It was just that consumers really didn't have that urgent demand for these very high data rates yet. And at the same time, like, these networks are not straightforward to deploy. So we'll see how it goes now. Now we're basically at this second stage where sort of 802.11ad came a little bit too early. 802.11ay, the successor, is targeting slightly different use cases. And at the same time, we have deployment experience from the first 5G millimeter wave networks Primarily in the US, they were very early with sort of rolling those out. Verizon was really at the forefront there. And now other networks have caught up. T-Mobile, AT&T are now, like at the beginning, they were sort of ridiculing this a little bit. And now they're starting to deploy those networks as well, in fact. And a few other companies are active there, like Facebook is having the Terragraph project. So the important thing from this is that now we're actually having feedback from real deployments to the research community. And that is something I think is extremely important to see what really is the performance, what really are the performance issues in real network deployments to make sure that research is going in the right direction. It doesn't solve problems that are not really real problems. And now in terms of where we are from the research side, what works well, and those were really sort of the first research issues that people have looked into. At mmWave, you have directional communication, which means that you have antennas that only radiate in sort of one specific direction, which means that you need to align those antenna beams, right? So a lot of the very early research on mmWave was looking exactly into this. How do you align efficiently the antenna beams? And by now that's been solved pretty well. So that even in mobile scenarios where whatever you have persons walking, cars driving, this is something that works well enough, right? You can do beam training, you can align those beams fast enough for the link not to break, as long as there is no blockage. Blockage really is an issue. As soon as you have a person or an obstacle blocking the link just goes away. So that's where we are right now. Of course, there's a lot of research happening beyond that, and I guess the other panelists are going to talk a little bit about this. In my view, what's missing, what really are the issues that need to be solved for more widespread adoption is network resilience would certainly be number one for me, right? Because that's something where if your link is mmWave gigabit per second and then suddenly drops to 0 to something very low, the user is not going to be happy, that's for sure, right? So if you want widespread adoption, you need to solve this issue that links at mmWave break. And you don't only have to solve it, you have to solve it with very low overhead, right? You cannot afford a lot of sort of unused backup capacity. You can have multi-connectivity to multiple base stations, but at the same time, of course, that also introduces overhead of maintaining multiple links. So you have to see what's the right trade-off there. And like I said before, blockage and especially also self-blockage, where your body is facing the base station and is basically blocking the link, that's really an issue. And how to recover from that very quickly is very important. What I also think is not quite important yet, but will become important soon, is efficient algorithms for large and dense deployments. So what I said, what's solved is single link beam training. But if you have very large, very dense networks, then the beam training overhead quickly scales up. And at some point that becomes unmanageable unless you have sort of more intelligent algorithms. And of course, researchers are working on that. One issue here is that the channel quality is only known after you do beam training, right? So then, of course, you can't do beam training proactively with all possible base stations just to figure out which one is the best one. That would not scale. You have to do something slightly more clever. And now, because of the very wide bandwidth, a lot of different applications will become possible that are much, much harder to do. Not impossible, but much harder to do very accurately at lower frequencies. So localization, tracking, sensing systems, where basically just from the communication itself and looking at the channel, you learn a lot about what's happening in the environment. And that will allow like joint communication and radar, joint communication and sensing applications that are just starting to be developed. What's clearly missing is real world experience with more complex and compelling use cases, right? So whenever you see mmWave papers that motivate why you need this, you often hear applications like AR, VR, vehicular networks, autonomous driving, Industry 4.0, systems where you have like lots of sensor data that you need to offload from those sensors, right? Especially in vehicular communication. But those are not really there yet to the point where you have information on how well this works from real deployments. You have it from 5G deployments that use mmWave links just to a normal user device so that the handset can get and gigabit per second data rates, which of course it's nice, right? But you have few applications that really use that yet. And so what's really missing is a little bit, what are the demands, what are the requirements of these applications, and how well do they work in the real world once they are deployed? Now, for the rest of the few minutes that I have, I quickly wanted to talk about what we are specifically looking into. So one of the things that I think is very, very important for researchers and for like to drive millimeter wave networking research is to have good test beds. And that is something that for many years has been a big problem, because it's very, very hard to build good millimeter wave test beds. And we've spent a lot of effort and many years to try to address this. So also for the discussion later on, I just quickly wanted to throw out what we have been working on, what's been developed. One thing that's very, very new, it will appear in MobiSys 2021, it's not quite out yet, is an open source platform for MIMO experimentation. And that's something that we're quite proud of, that took us a long time to develop. One of the issues really is that it's very difficult to build software-defined radio platforms for the very high end, right? So of course, like people are familiar with USRP, and if what you want to do is LTE or 802.11n like implementations, that's not very hard, and you find ready-made implementations for this. But once you want to go to very high order MIMO or millimeter wave MIMO, it gets very difficult, and there are sort of some custom solutions, but you don't really have a widely used testbed platform. Now, we've started to build a system based on Xilinx RFSoC, and this seems to be a very nice platform that gives you extremely high performance at a price point that's very, very reasonable. And the system that we developed is very flexible. So you can run it as a 4x4 millimeter wave MIMO system with 2 gigahertz of bandwidth. You can configure it as an 8x8 sub-6 gigahertz MIMO system, right? So it supports millimeter wave as well as sub-6 gigahertz, which is great because if you work, for example, on 5G or 6G at multiple different frequencies, a single testbed would support this. And you can even mix and match. So you can even have some streams that support millimeter wave, 2 gigahertz of bandwidth, and some other streams that support sub-6 gigahertz. So you could have, for example, a 2x2 millimeter wave and a 4x4 sub-6 MIMO network operating on the same single FPGA at the same time. And so we think that's something that in terms of functionality is very, very interesting. We have a few things directly implemented on the FPGA, packet detection and channel estimation. At the bottom, you see one of the pictures with the RFSoC board in the background and the millimeter wave antennas in the foreground. And yeah, we'll continue developing that system. But that's one of the platforms that we basically just are about to release. It will be released open source. And if you're working on millimeter wave experimentation, that's certainly something where we'd be very, very happy if you take a look at it. And if you can use it, that'd be fantastic. We've also been working on off-the-shelf deployments, just because sometimes what you need is really a large deployment or standard compliant hardware. And then the easiest to do is don't use software-defined radios, take normal off-the-shelf devices. And then, of course, the problem is you want to use them in a certain way. You want to change their behavior. And so here, that's something that we did together with TU Darmstadt. We've worked for a while on porting OpenWRT, which is just sort of an open source embedded Linux to those routers, and to do firmware patching for the millimeter wave drivers so that you can do your custom beam training. You can change the beams, select which beam you want, and then do sort of experimentation with this. So here we even build test beds of 30, 40 devices, which of course, yeah, you can only do such large scale deployments at a reasonable cost with such off-the-shelf devices. And very briefly at the end, we're also working on NS3 and have an implementation of AD and AY for NS3. And yeah, again, that's like whenever it's difficult to do something in hardware, then of course, like running software simulations is the next best thing. So with that, let me conclude. I'm sort of out of my 10 minutes. This just to quickly throw out what we've built for the research community. And I think it's very important to sort of work together on building such tools, improving such tools to make sure, yeah, basically nobody does the same effort twice unnecessarily. And yeah, towards the end, just very briefly, the discussion topics. What we wanted to talk about later on in the overall discussion would be important open research questions, of course, for mmWave, what each of us thinks would be interesting to look at, lessons learned from first deployments. Then very important from this directly related would be availability of real world measurement data, because that can be very hard to generate and very hard to have access to, especially if you're talking about real deployments. And testbed and platforms, I've just talked about it a little bit, but I think there are many different and other efforts as well, and would be very nice to see what the community can do to pool those efforts to get the most out of these testbeds. So with that, let me conclude, and we'll kick it off by handing over to the next participant, which is Sundeep. Sundeep, I'll stop sharing and the floor is yours.
Okay. Sorry. All right, you guys see this?
Yep.
All right, well, want to thank Joerg and Manu and everyone for organizing this and giving me a chance. I just want to quickly look at where we are in 5G. That seems to be the theme here. So this was a photo from a journalist who had taken a 5G phone out in Chicago last year when that was the trial network for Verizon. Of course, Verizon has since then made it available nationwide. And this is, if you haven't seen this paper, this is a great paper from a group in University of Minnesota, Twin Cities, where they actually ran a pretty detailed test of 5G, also in the Chicago trial network for last year. And, you know, a lot of that promise we see occasionally. So you can read this either journalist article or this paper, and you get occasionally greater than gigabit per second throughput, but you also see some very serious problems that we kind of anticipated. So for one thing, you see that the link drops occasionally and has to fall back to 5G, and you no longer get anywhere near that super high throughput. And that raises sort of problems that we knew that we were going to face. So one is that a lot of those drops are due to blockage, and actually that paper is graded. It has a lot of blockage experiments. And so we knew this is going to be a problem for mmWave links. The other part is still the power consumption. The devices, particularly last year, even though with a lot of optimizations, are still burning a lot of power. And as I think Joerg was mentioning, if we want to try to overcome the blockage, we need much higher density of network deployments. And that's particularly hard at least in the US, where we don't have a lot of great fiber coverage that we can deploy cells. If we think back to problems that small cells faced about 10 years ago, it was very similar. And I think that the other question is that there's not really yet been a very compelling use case, although maybe this will change going forward. And I think these are maybe some of the things that I would like to talk about in this panel. So maybe I'll just quickly talk about some of the research our lab is doing. On the power analysis, this was a graph from one of the papers at 140 gigahertz, but we've also done this at 28. We've been looking at a lot at the hardware with some circuit designers to try to understand where the bottlenecks are in designs at the mmWave parts. At least for fully digital designs, but a lot of the contention was in the ADCs, but we've actually since realized there's a lot of actual bottlenecks in the mixers and other components, which we can talk about. So I'm happy to talk about this. We've also been looking at going out to higher frequencies here, as shown in 140 gigahertz. And we can talk about this as well. There's also a lot of discussion. Joerg didn't mention it, but for AI and ML, and it's kind of interesting, I think, in both two regards. A lot of the discussions, one way or the other, about use cases somehow end up connecting to using wireless for mobile AI. And that is basically to try to use it for computational offloading and to access data in the cloud. And I'm happy to talk about some of the stuff we've learned so far, both with collaborations with roboticists as well as also on UAV links. The other part is actually using mobile and machine learning for overcoming some of these problems. I don't think it's going to be a game changer. It's more on the optimization side. But one of the interesting things that comes out of that which touches on what Joerg was mentioning. It's about where we get training data from. And we've been using a lot of extensive ray tracing, and I can talk about this, and these are from some of the papers that we were talking about. The other thing about use cases, what are going to be the compelling use cases? So as Joerg mentioned, we have VR and AR. If we go even to higher frequencies, one of the possible ideas, various things have been floating around. There's an Ericsson system out, or now at least in prototype, for what's called line of sight MIMO for very high speed point-to-point links. There's also for backhaul, and then also for UAV. So I'm just going to leave it at this, and we can talk more during the discussion.
Thanks a lot. Next one would be Michele.
Okay, thank you, Sundeep, and thank you, Joerg. So here's my presentation. Should be up there. So our approach, has been to recognize that there's a lot of good research on many aspects in these millimeter wave systems. Mostly devices or measurements. There are also some networking studies based on very simplified versions of the physical layer of what happens at the propagation level. And so what we realized that in order to assess the performance of these systems in a more complete way, you really need to take an end-to-end point of view. And you need to also take a full stack point of view. So you can't just focus on just the physical layer to push the limits of the bit rate, but you have to evaluate that in a full framework where the actual user performance is measured by taking into account all the components that belong to the network and significantly affect its performance. Hence the need to have a tool that allows us in a scalable but precise way to capture this complexity and give us the right information about this performance at the application or user level. So that was part of our effort. We realized along the way the channel models are key because too often the channel is not captured precisely, and this compromises the meaning of the results you're getting. And so we've been working in that area as well. And then, we try to apply this knowledge or these evaluations to some key scenarios. Joerg mentioned those. Clearly, there are many that are not yet real, but they are actively being studied. And it's important to be able to say something about these scenarios even before they are actually deployed in the real world. So the end-to-end simulation, together with NYU, in fact, Sundeep was one of the authors in many papers that we published on this, an end-to-end simulation framework where we recognize that the network is much bigger than just the physical layer of the radio access network. And so this comes with an open source simulation suite, which is based on NS3, which incorporates millimeter wave propagation and and many of the useful protocols, including TCP/IP stack and everything. And so this gives you a very detailed tool, which allows us to take into account properly interference, errors, propagation issues, fading, beamforming, and all that, and bring all this complexity to the application layer to give an evaluation of what happens and what the user actually experiences. Now, one piece that we are including now is a channel model based on ray tracing. Here, the issue is that if you want to be accurate in the channel model, then of course that brings a lot of complexity. And if you want to evaluate networking performance, that needs a lot of simulation. So you are facing this big trade-off between complexity of the tool and execution time of your simulation versus inaccuracy. And so being able to characterize this trade-off and make choices in simplifying models while not compromising the accuracy is a very important step. And so we are collaborating with NIST, the National Institute of Standards and Technology in the US, about this. They have data sets. We have a ray tracer that we built together with them, which is open source, and it's actually given at this GitHub link on this slide. So there are things that are happening here, and the hope is that eventually we'll be able to provide a good tool which is both accurate and scalable, allowing us to perform these evaluations on a large scale using a full stack perspective. And then, we examined a few key scenarios. I put the slides more as a placeholder than something I have time to talk about. But the important thing is that we try to collaborate with key players. For example, here we have a collaboration with Toyota in the US, where we are trying to evaluate this kind of performance in a vehicular scenario. So again, we have an S3 implementation for the V2X use case, including side link, which is an important piece in this area. And we're able to produce results, as you can see here in the slide. So throughput and delays versus distance between vehicles according to a number of different scenario, urban versus highway, and different modulation encoding schemes. So we are able to provide some indication of what you can achieve there. And I put a paper down here in each of the slides, so you can have a pointer if you're interested in learning more. Another key scenario is non-terrestrial networks, very important also for 6G, the upcoming research involving not only satellites, but any flying vehicle, be it high altitude platforms or drones or UAVs, things like that. And here also there are trade-offs. Millimeter waves, on those long distances will suffer because of propagation. So it's important to be able to say something about what is achievable and how it is achievable. Multi-layer hybrid architectures means that you have different altitudes that may work together. And so we have results here that you can see here, where we compare different constellations, different choices, design choices for different elevation angles, and studying the trade-offs, which show that this is actually feasible. So a millimeter wave can be used for satellites and for these non-terrestrial networks if you know how to do it. And so it's important to understand the different trade-offs there. And finally, IAB, integrated access and backhaul, is another use case which is of interest. It's probably, of the three, the one which is more advanced in terms of deployment. This is seen as a good way of providing access and backhaul using the same frequency band. And so we have a backhaul which is not only wired, but it has a wireless part, and the wireless technology which is used for the backhaul is the same as used for access. So the question is, how do the two systems work together? How do they interfere or they coexist? And here also we have an NS3 module to study this, which is available there. And we have studies that show that you can actually achieve very good performance doing that despite the level of interference. Once again, the focus here in all of this, and let me conclude with that note, has been to try to include detailed propagation information and models while trying to keep scalability in mind, so that you can produce statistically significant results using simulation at the network and protocol and application layers while having a full stack end-to-end view. And with that, I will leave the floor to the next speaker, which I believe it's Xinyu.
Okay, hello everyone. I will briefly share our experience in designing and building experimental platforms for millimeter wave research. So we all know that software radio platforms have a great impact on research in wireless communication and sensing in the past decade. A lot of the research outcomes have gone into standards such as full duplex, uplink MIMO, and wireless sensing. On the millimeter wave side, the research platform is still a bit lacking so far. We have seen a few experimental platforms, but there are various limitations such as cost, scalability, and also flexibility. In the past few years, my research group had spent a lot of time building experimental platforms. We started back in around 2013. We built an experimental platform, software radio called Widmer, running on the 60 gigahertz band. It has a horn antenna. which is mechanically steerable. So it's still not the same as a real commercial millimeter wave radio with the phased array antenna, but at that time we can already emulate a typical phased array by using simulated beam patterns and also by using directional channel scanning. Later, we had a second version which has a phased array custom built. However, the phased array is still very small, only 4 elements, still far from the features of a typical commercial millimeter wave radio. The most recent development is mmCube. It's a millimeter wave MIMO software radio platform. It has a much larger phase array compared with the previous versions. In total, it has 256 antenna elements. It's also a MIMO software radio supporting up to 4 channels simultaneously, which can be used to test some of the advanced MIMO millimeter wave communication and sensing technologies, such as hybrid beamforming. The basic idea behind this platform is we can actually hijack or reverse engineer a commercial millimeter wave radio and separate its phased array front end from the baseband. By doing that, we can gain control over the phased array. We can control the codebook, beam pattern, and beam switching. And we can also gain control over the data channel. We can send and generate arbitrary waveforms through the baseband, through a programmable baseband, such as an FPGA. Our current development is using some commercial FPGA platforms and also commercial software radios as the baseband processor, such as Xilinx FPGA, ultra-scale FPGA, and also WAP, USRP, and so on. The typical low-frequency software radios can be reused as the baseband processor. Ongoing development involves using Xilinx RF SOC as the baseband, which has a much wider bandwidth and higher sampling rate. We have also developed some reference implementations, such as the OFDM MIMO millimeter wave communication and also FMCW radar sensing module using MATLAB. But real-time implementation based on RF SOC can also be feasible and is under development. This is a brief comparison between the early versions of millimeter wave software radio and mmCube. Of course, this doesn't include what Joerg just mentioned, which will appear in MobileSys 2021. So compared with the previous versions, mmCube features a much larger phase array, as I mentioned, and also its cost is surprisingly lower because we are using commercial millimeter waves phase array front end directly. And in fact, the majority of the cost is actually in the baseband processor, which is typically a high-end FPGA. We also reused the front end of mmCube software radio to build a larger scale experimental testbed, the mmWave V2X testbed on the UCSD campus. And we conducted a lot of experimental studies to characterize the mmWave V2X network. And we found that surprisingly, it's easy to manage beams in mmWave V2X scenarios even under high mobility because of some of the special structures in the mmWave V2X channel. To briefly summarize, we have gone through a long journey to develop millimeter wave software radio platforms and learned a lot, of course. I hope we can share the millimeter wave mmCube software radio with the research community so that other researchers can reuse it for wireless communication and sensing research purposes. In fact, we have distributed the replicas of this software radio to quite a few research institutions, and we are making more replicas to share with other research teams. Okay, with this, I will conclude my talk and can switch to the next module.
Fantastic. Thanks a lot, Xinyu, and thanks to all the speakers for the remarks. And remarkably, this is a very professional group, so we're very close to being on time. So kudos to everyone. So now we want to switch over to a little, Q&A and kind of some open topics. So we have a couple of questions. I'm just going to throw them out there for the panel to consider, and then Joerg, it's up to you to ask any follow-on questions you wish of the panelists. So one is around, the questions around talking about smart materials, smart channels, and smart spaces for millimeter wave and terahertz research. So I guess this is looking at, all the way from the futuristic materials for maybe the RF antenna systems, subsystems, and then relationships of the materials to the channels for millimeter wave, and now looking up to true terahertz. So if anybody on the panel wants to react to that.
Maybe let me quickly start, and then I'd hand over to the others. So I think that's a very good point. I think we're at two different points here for the different types of networks, right? So normal millimeter wave networks, 28 and 60 gigahertz, there we're really in the deployment phase, right? So this is something where you have products, and a lot of the research now is how do you make this work in a real scenario at a point where the applications can actually sort of, basically you're fulfilling the requirements of the applications in terms of resilience and reliability. And that really involves sort of a lot of research across all the layers of the stack, especially for millimeter wave networks with their very special characteristics. And then what was mentioned here in terms of smart materials, smart spaces for millimeter wave and terahertz, I think there we're at a different stage in at least from what I've seen so far, right? So that's much more early stage, where it's really about how do you get this to work in the first place, right? So like we're still very far from how do you optimize it for a specific application. This is much more like how do you build a terahertz antenna and then connect it to an ADC so they can actually send a waveform efficiently and so on, and make use of the theoretical extremely high capacity. I don't know what's the view of the other panelists on this. Xinyu, Michele, Sundeep, anyone has an additional view? Yep.
Maybe I think maybe the question was also relating to reconfigurable surfaces. That's not my area, but I think it has some exciting possibilities. But what I think we need to understand or at least from my perspective, is to understand how it influences the deployment model. So you can always, of course, just create more cells. But then there's the other option, in which instead of creating another transmitting point, just create a reconfigurable surface, which can actually reflect that. And I think that's a great open question to know what are the trade-offs for that between deploying more cells in a greater density or creating these reflectable surfaces, reconfigurable surfaces, to understand that trade-off. The other thing that which is exciting to me about the reconfigurable surface is essentially it's a very wide aperture antenna, which means that you can actually end up in the near field of that much more easily, which means you can have actually multiple streams even on a point-to-point link. And that may be advantageous if there are demands of very high data rate applications or for getting greater spatial multiplexing amongst users. So I think this is a kind of early stage, and I think what we need to know, for at least I would like to know, is just to get some kind of deployment model. We've had, we came to millimeter wave with decades of experience of knowing how cellular networks are deployed, and we could just map that on when we try to look at millimeter wave. We know the cell densities and what are the parameters, but it kind of opens up another whole can of worms for me about what are the deployment models are. Maybe that, so that's my perspective on it.
If I may add one thing, I also agree that being able to characterize how these surfaces behave will be important. And from my perspective, that of a networking researcher who would like to study the system's performance, starting from usable models of what happens at the propagation level, and essentially instead of having one type of devices, then you can have these surfaces used jointly with maybe some regular good old relays or some more advanced relays, and how they produce signals, how these signals interfere, how they combine. and how you can design networking systems and ultimately provide application performance in this environment is, of course, a very challenging, very interesting question. So what I'm seeking would be models from people who study materials and surfaces, models that I can use at the signal level, but also at the interference level to be able to plug this into my NS3 or whatever framework to produce usable results for system optimization.
Besides new hardware mechanisms such as the reflection surface, I believe it's also very important to study new network management mechanisms, such as how to coordinate low frequency and high frequency, because it seems based on existing measurement of millimeter wave networks, the network management part is just overreacting to some of the limitations of millimeter wave, such as beam switching. There's frequent switching between low frequency and high frequency, which is undermining the network quality. So probably we should look into the higher layer and see whether any slight modification or better adaptation is needed.
Mm-hmm. Yeah. I think those are excellent points. And just to briefly add, I mean, the deployment aspect that Sundeep mentioned, and also Michele in terms of the properties, I think that is super important from a practical perspective, right? So from the research perspective, no question, they're very important, interesting research questions to be solved in that space. How do you make this work and how well does it work? But then from a practical perspective, of course, the question is always, like, people will know how to deploy access points. And it's very easy, right? You build out lots of those, right? And whether you deploy 10 or 20 or 30, I mean, the additional cost is not that high. So then the question is really, are these smart reflective materials so much either orders of magnitude cheaper, right? Because then it's something where you need volume for this to financially make sense. And are they easy enough to deploy, right? It's easy to just stick an access point to the wall. How do you actually sort of fix the smart reflective surface? Does it have like a similar ease of sort of just attaching it to a wall? How large does it have to be, right? Because if you need whatever, 2 by 2 yards of a smart reflective surface in terms of deployability, just to make sure that like you can easily hit it with a reflection and it reflects back to where you want, right? That very much restricts the deployment scenario. And then maybe you just have too few cases where this really makes sense, right? So I think this is something where at least I've looked a little bit at it. And for me, that's not clear yet, right? If basically, if the gains are large enough that as an operator, you would, it makes sense, right? At least sort of from what I can see now. Of course, it's also very early stage, and it could be that those improve a lot and become much more flexible, so that it really makes sense to deploy those instead of access points. But yeah, I think this was an excellent point also, Sundeep. I see there's another question from the audience, which was about the hardware requirements for 1 or 2 gigahertz. That was directed to you, Xinyu.
Yeah, I think that one, if it's related to a specific one, Xinyu, if you're able to just type it in the chat window or point for that answer, we can take that. I'd rather keep at least the panelists engaged in a broader question. There's another one there that Joerg, or if you can take another, go for one of the questions you had, and then we can take one more from the audience. So I think the open research questions would be very good. I think for the students in the audience or young faculty and others who've joined us, I think they're really looking at what are the main issues that you're looking to solve, and what maybe the really cool testbed infrastructure, radio system subsystems that you've been developing, what kind of new research areas that they would enable, and what are the major sort of pain points that people should be focusing on. That'd be maybe a good place.
Mm-hmm. So I'll hand this over directly to the other panelists in terms of, so that was one, I think, of the important questions. What do you think are the most important research questions and open pain points, like Manu said, that still need to be addressed? Maybe we'll just do a quick round in the order of how I see you on my screen, with Sundeep, Michele, and then Xinyu.
I think for me, the big questions are use cases, because that's the, how we're going to use these systems, because there's not been a compelling use case. And one of the other big ones is really the power consumption and form factor for these devices.
Michele? Are you muted?
Sorry. Yeah, I think the big issue is how to study this system in a holistic way, so that you can bring in all the aspects and not be caught by only a piece of the system, and you can really provide the overall performance. And then I actually concur with Sundeep that the energy issue would be a key factor in the success and deployment of these systems.
From my perspective, it seems the coverage is a major issue currently with mmWave. How to achieve reasonable coverage at low cost, that perhaps is an important question from both academic and industry perspective. I think this will need to be resolved somehow. Besides this, I think there's still a lot of open problems on upper layer, as I mentioned. How well does the higher layer protocols such as TCP and applications such as real-time video work under the channel dynamics created by mmWave and created by a conjunction of mmWave plus low frequency? This is still open question.
Yeah. And maybe to add from my side, I think that's really from my perspective, one of the main points, like network reliability, resilience, right? Because we know that mmWave networks break and there will be blockage, and you will have to work around this with multi-connectivity. And to get to the point where it's really acceptable for the user, right? Where you don't have the user calling the operator, look, my mmWave link breaks all the time. I want to go back to 4G because I don't see any point in having this flaky connection, right? To get to the point where the user is really happy with what he sees. And we've seen it in the little picture that Sundeep showed, right? You had fluctuations between a gigabit and then, what was it, 50 megabits, 100 megabits, right? And then you run TCP on top of that. It's going to be very difficult for TCP to get good performance there, right? So it's not just how to get reliability, which, okay, you have to intelligently like use your high frequency and low frequency network and ideally connect to multiple base stations simultaneously to make sure that like at least one of them still has a line of sight connection. And at the same time, it becomes a network management problem, right? What you want to do is you want to move all your users to high frequency as much as possible so that your low frequency resources that you typically always have as a backup are free for the users that need it, right? So you lost your mmWave 5G connection, but the low frequency 5G is pretty empty, right? So then you get a gigabit there as well. But of course, you can't have that for 100 users. You can serve like whatever, a handful of users maybe, right? So then it's not just a multi-connectivity issue, but it also becomes a network management issue. And I think sort of optimizing this in real deployment so that it really works well, I think that's really something where there's still quite a bit of work to be done.
Yeah, and in addition to that, and to compound with that, I think the time scales involved are getting more and more challenging because everything's more dynamic. The super high data rate means that in a very short time many things happen, and if you lose the network for a small time, it's still a lot of bits. And the very strict latency requirements that are coming up, 5G, 6G, everything is so challenging at the time scale level that even the physics of propagation gets involved, right, at some point. And so this is really, really hard.
And that's super interesting because, I mean, the way you figure out that the link broke is typically still, well, you send data, no ACK is coming back, and then you realize that the link broke. But if you want to have ultra low latency and you want to sort of avoid that, you have sort of a 10 millisecond gap where there's just nothing, and then you figure out things broke and you move to another frequency or something, right? Then you need to know much, much more quickly, much better what's going on in your environment, that you don't have to rely on looking at packets, whether they arrive or not, but you actually monitor the environment and see what goes on, and you immediately see that now there's an obstacle. I see a reflection coming back where there was no reflection before, for example, and for that reason, I know the link broke. I don't even have to try. I see the environment. I think that's a very important and interesting research direction.
Yeah, it may be a combination of a very short control loop, much shorter than currently is, and maybe some predictive ability and intelligence that are able to predict things before they happen. So it's not reactive, but it's more proactive.
And then I think there was also a very interesting question from Alain. So let's move to that one. That question was about deployments and why Europe is lacking behind the US. Why was US first? And Europe so far hasn't really followed suit. So I don't know, Michele, if you have further insights, I can say a little bit about it.
Not much actually about deployments in Europe. I was reading the question and wondering, but not so familiar with the commercial deployments or lack thereof in Europe. I mean, in the US, there seems to be a big push from the very beginning. And in Europe, we're not seeing that, although, in many cases, the players are actually global players that are both there and here. So I'm not sure why. And also maybe, in big cities in the US, things are maybe more appealing for these deployments, although, we have big cities in Europe too. And in the US, maybe there are more open spaces that are hard to cover with millimeter wave. So I'm not sure why this is the case.
Yeah, and I must say, I don't know either. And of course, the operators won't tell you, right? They're just like highlighting that they're doing 5G and they're at the forefront. And now why not millimeter wave? Of course, nobody's going to mention what they don't have. My perception is a little bit that, I mean, this is mainly at this stage something where you just want to show technological prowess, right? You want to show that you're at the forefront, but the business case is not there, right? Verizon, I'd be extremely surprised if Verizon makes money off of them. I mean, the deployment cost is so massive, right? It's going to be many years until they make any money out of this, right? So it's also something where unless you are like sort of forced to do it to appear very technologically savvy to your customers, I mean, the longer you wait, the more money you save because equipment is getting cheaper. You don't have the deployment cost yet, right? So also my perception is a bit, there's not that high of a pressure in Europe for operators to show that they're doing this, right? And then it's just a matter of, I mean, the use case isn't there anyway, right? It's not that customers go to operators and say, I want my millimeter wave connection because I've got an application that needs these data rates, right? It's more something where now really it's sort of the cutting edge users that always want the newest technologies. They're happy to try it out and they're happy that they see a gigabit on their mobile phone. But so here, I think this is largely due to lack of business case yet, but sooner or later this will come.
Are there different models for spectrum usage or spectrum licensing or for between Europe and the US that maybe one area, right?
I think it was partly, we probably have to start wrapping up soon, but I think there was more mid-band spectrum available in Europe. And that's something that the American operators have complained about. But also, there was a lot more skepticism about the business case, as Joerg said, that didn't motivate. It's not a technical reason. On the other hand, I think going forward, Europe will be at a big advantage, as well as Asia even more so, because the fiber connectivity is much greater and the cell site deployment cost is dramatically lower. And that's something we in the United States will have to address, and that goes to the coverage and deployment issues.
That's a great point, Sundeep. And so we are getting close to, sort of wrapping up. If I can just maybe in a yes or no, I think this is a pretty interesting question that was posed. So all these open research challenges that are up there, is it real to imagine having or investigating terahertz bands in 10 years or so commercially? So I know all you guys are also sort of in your forward, looking at the greater than 100 gigahertz and actually close to 2 terahertz work. But what do we think about the feasibility of terahertz based on what your initial research tells you? Very, very short answers if we can go around the table.
Maybe I'll start. I think it's feasible from a technical standpoint. Again, when it comes to a use case, I think we'll see it in niche cases like backhaul. I don't know whether it'll be ever useful in like to a smartphone.
Yeah, feasible and worth studying, worth experimenting. Yes. Out in the field in 10 years, not sure.
I would say that at least it's worth research, and we probably shouldn't just wait for that to happen before it actually has commercial use. We should just look into the feasibility and potential first.
My view is also that sort of millimeter wave is going to take a bit longer than expected to be sort of like the standard technology to be used, because you need the bandwidth, right? And that also means that, of course, then terahertz is also going to take longer. So my guess would be on the handset, no, like Sundeep said. But for niche applications, certainly yes, right? Sort of very short range, extremely high speed communication on chip or something for that, it could certainly be a very interesting use case.
Awesome. Thank you so much. So yeah, so for those, whoever has asked that question, I think that is pretty much the next frontier. It's being very actively being discussed, debated. So look out for that conversation. And there are plenty of conferences that are happening that are looking at terahertz that are coming this fall. So with that, I want to take this opportunity to thank the speakers and panelists. Sorry, Antonio.
Manu, just one small comment. You can continue this discussion in the Slack channel. We will make sure that any question posted in the Slack channel is forwarded to the speakers.
That's right. Thank you. And then the session's recorded. The recording will be on the website. We'll try to put the slides from the speakers on the networkingchannel.eu as well. And then just a plug for the next event in 2 weeks on the 21st of April. We're going to continue the theme around 5G Next G, and this time looking at the Open RAN concept with the speakers from industry and academia, as well as these open consortiums led by Guru Parolkar from the Open Networking Foundation here in the US, but a nice broad forum. So hopefully you can join us in 2 weeks, should be very exciting. And this will actually have more of an industry deployment flavor, end-to-end network, not just the wireless domain, but also network compute core, as well as different variable concepts. So with that, I'd like to wrap this session up. Thank the speakers and the panelists. Thank you so much for your time, and thanks to all the attendees. This was real fun. Thank you so much.
Thanks.
Thank you.
Thanks a lot.
Bye, everyone.
Thanks.
Thank you, everyone.